we like to do what water does. You know, you can float in water, you can go deep in water, and it doesn't push on you any harder anyplace else. Dry flotation is really a synthesis of flotation. So when you get into understanding of how a fluid acts on a person floating in and suspended in a fluid, you have to understand that there's low surface tension, 6 degrees of freedom, low friction, and a constant restoring force independent of depth of immersion.
There's surface tension there, but it's very low. So you got to be able to get immersed or penetrate the surface. When you have a person sitting on the cushion, you're always working to get them as deeply immersed as possible. You really want them to enjoy as much surface contact as they could possibly get.
A water molecule can go any place it wants to go. And that's why water can wet any shape that's presented to it. 6 degrees of freedom is basically recognizing you got an axis system in space, and there's 3 axes. There's an X, see, it's an X, a Y, and a Z. So when you're in space, you work with those kind of axes. Or if somebody's floating in water, they can rotate around any of these axes. So one of the degrees of freedom is being able to go up and down these axes, back and forth. So you're free to do that. You go up and down, that's 3 degrees. The next degrees of freedom is to rotate around the axis. So when you do that, you added another 3 degrees, so the total is 6 degrees of freedom. So if you look at an air cell sitting here, which is a thin, flexible rubber construction, then the air cell is free to go up and down. It's free to twist. It's free to go back and forth. So it has 6 degrees of freedom.
And we do that with all the individual air cells made out of soft rubber, neoprene rubber, that allows the cells to shape and form to the body that it's contacting. The other side of that is friction. You really don't want a lot of friction. So we treat our air cells to be slippery. Friction is the only method of inducing shear loads on the body, and shear loads then induce deformation. Low friction reduces the shear loads and therefore reduces the deformation that induces a ischemia. Tissue deficient wounds depend on a granulation process where the exposed capillaries basically create little nodules at the end of the capillaries, and they are slowly but surely recreating tissue. And if you can support that without knocking off the nodules, because that's what happens with these air cells. They basically roll with the tissues, and they don't drag across the tissues. That's a whole other proprietary process that we use to create low friction cell surface. In essence, we're creating flotation, not using water. Buoyancy within a fluid is very, very steady, very constant. No matter how immersed you get, the buoyancy forces are about the same. So you need a constant force, restoring force to support the person. So no matter how deep you get immersed, it doesn't push back anymore. Normal cushions have a spring rate, so when you push into them, the further you push into them, the harder they push back. So when you have a disabled person, you're dealing with, they're emaciated, atrophied, bony prominences are dominant, and you don't want that bony prominence to see more push than the rest of the skeletal system. And the advantage of having a pneumatic system like this is we can basically control the equivalent density of the fluid by changing the air pressure. So we can theoretically support just about any weight that might be presented to the cushion by adjusting the internal working pressures. So it's a much more flexible arrangement as opposed to having a bucket of water When you get into what makes things stable, because people get confused, at least I think they get confused with respect to rigidity versus stability. And stability is just a understanding that if a body receives a disturbing force, and when the disturbing force is removed, the body comes back to its original position. So that's stability. When you have basically a fluid that you're synthesizing, that people are sitting on, it does have drift, positioning drift. So to eliminate that drift, we interpose a valve system called the isoflow valve and divide up the pneumatics into quadrants. So now you can not only stop the drift, but now you can hold a person in a position. So when you get into positioning people, you're always seeking an optimum position. And the body responds to ever what happens and accommodates certain things, but it needs to have a possibility of being repositioned. So you open up the isoflow valve, and the thing that's different about using what we call the quattro cushion is you move the person to the position and not adjust the cushion to affect a position. Most disabled people have a hard time with correcting themselves on their own. There's only so much you can do through the pelvis to do positions and achieve stability. But with a quattro cushion, it holds that pelvis in the same position. So once you get into the cushion and get immersed into it, you try to contact as much of that skeletal system as you can. So if we need to have more push or more position to correct positioning, more forces, then we open up the valve, get the immersion side squared away so to optimize the pressure settings, close the valve, and then hold a position that we selected. And the nice thing about this is that as the time goes on, you can reposition the person without taking them off the cushion. The cushion just tracks along. This system has basically a pneumatic feedback paths, and it keeps readjusting for that new shape. So you're chasing a target all the time, moving target. So seating is an interesting challenge.
We're always dancing with the trade-offs between stability, position, and therapeutic function.
I think of it as a triangle.
When we're dealing with somebody sitting in a cushion or a chair, whatever it may be, there's always these trade-offs between, you want to be mostly therapeutic, you want to be mostly stable, or you want to be mostly positioned. So we have been working with a valve system to control 4 quadrants in a cushion, the isoflow valve, so that we can do most of that. But once you position somebody over and then you lock up the valve, then you achieve stability and positioning, but the trade-off is therapeutic. It's not as therapeutic as a cushion that we make that has free flow with everything.
I guess the only question I would ask is the isoflow valve gives us some, when you started explaining all that, I thought, well, ideally you want a product that can be suited to whatever this particular person needs the most. Does this person need stability the most, or do they need therapeutic value the most? That you had a product that say, okay, for this person, I can adjust my product to do more therapeutic work. What you sort of said when you said a free-flowing cushion would be more of a therapeutic
Which
cushion.
is where the isoflow valve is open.
Yeah.
You got 2 modes of operation with the quattro cushion.
So that's what we were going after, was satisfying all 3 of these points.
Yeah, exactly.
Yep. Makes sense.
And trying to make it convenient to do.
Right.
Mr. Gravy, is there such a thing as a perfect cushion?
No.
No.
That was easy.
Everything's a trade-off.
It's blood flow, blood flow, blood flow. It's the key, and we do that by not changing that person's shape by very much. The shape does adjust with time and forces because we essentially move body fluids someplace else. That's blood, interstitial fluids, and so forth. So the body is very dynamic with respect to blood flow. And for every action, there's a reaction. You just can't get around that. So by maintaining blood flow for long periods of time, we hope and do quite a bit to support tissue viability. And tissue viability, I think, is a key perspective as to how we should think about things. So many of the academic people are focusing on tissue destruction, looking at tissues being destroyed close to the bone and things like that, which is certainly happens, but you really don't want to be there. You know, you want to be operating in a safe zone, and so I guess these are intriguing problems, but it's not where we want to be. We really want to be with tissue viability. You're compressing all those tissues, ducts, whether you're talking about a lymph duct or you're talking about the vascular ducts. So you're putting equal forces, compressive forces on all those. And if you really don't deform them very much, they can still have flow. So fluid flow is the key with maintaining blood flow, lymph flow, and then as you compress the tissues, they become closer and closer to the actual skeletal system that's there, in this case the pelvis. So that shape becomes more and more dominant as time progresses, and we're talking hours now, so that the shape that it gets exposed is more and more close to the bony protrusions, especially like the ischial tuberosity. And that gets to be the most difficult place to distribute forces. People want to talk about pressure redistribution. I don't understand that. I don't believe that's what we're talking about. It's all about force equalization. And if you utilize and equalize the forces, as a ROHO cushion does, then all of these areas see the same stress, essentially. You don't get any peak forces deformation.